Back in 1954, there was this surgical team in Boston that pulled off something that honestly sounded like entirely out of a science fiction novel.
Oh, absolutely. It was groundbreaking.
Right. So they took a healthy kidney out of a young guy named Ronald, literally walked it over to the next operating room, and sewed it into the abdomen of his identical twin brother, Richard.
Richard was dying of kidney failure at the time, right?
Exactly. But after that surgery, he lived for another 8 years. I mean, the plumbing worked perfectly, the blood flowed. It was just this complete medical triumph.
It really was an incredible milestone for medicine, but, it also kind of set up one of the most frustrating decades in surgical history.
How so?
Well, because when doctors tried that exact same surgery, perfectly executed on patients who were not identical twins, it was a total catastrophe.
Oh, wow.
Yeah, the stitching would be flawless, right? The organ would pink up. It would start working right there on the operating table.
Like everything seemed fine.
Exactly. And then within days, or honestly sometimes just hours, the recipient's body would literally rip the new organ apart from the inside.
That's the terrifying paradox of organ transplants, isn't it?
It really is.
Because we always think of it as this surgical challenge, like getting the blood vessels attached without any leaks. But they actually mastered the surgery part 70 years ago.
Right. The surgery was solved. The biology was the wall.
And that is exactly our mission for this deep dive into our sources today. We are looking at the invisible, just ferocious biological war that begins the actual second the surgeon puts down the scalpel.
It's fascinating and terrifying.
Truly. So we're going to explore why your body would literally rather die than accept a life-saving gift. And how doctors learn to negotiate a really fragile peace treaty with your biology.
And we'll get into the future, too, that mind-bending gene editing technology that might actually finally solve the global organ shortage.
Yes, which is the craziest part. But to start, we need to understand why those early non-twin transplants failed so violently.
Yeah, and for that, we really have to look closely at the immune system. We often talk about it as a standing army.
Right.
But it's actually more accurate to think of it as a hypervigilant surveillance state.
Oh, interesting. Not just soldiers, but spies.
Exactly, because its primary function isn't just to kill things. Its main job is to constantly distinguish between self, so your own biological material, and other.
And other could be like a virus or a bacteria.
Right, or a stranger's kidney, it doesn't really care.
Okay, so let me ask this, though. How does it actually know the difference? If a human kidney looks like a human kidney, how does the body know it's not yours?
Well, it comes down to something called human leukocyte antigens. Or HLA for short.
HLA, got it.
Yeah. Every single cell in your body is covered in these HLA proteins. You can think of them as these really complex, highly specific molecular barcodes.
Oh, like literally scanning a barcode.
Yes. And no two people on Earth, except for identical twins, have the exact same barcode.
Which explains Ronald and Richard in Boston.
Exactly. So your immune system has these patrol cells, primarily T cells and macrophages, just constantly roaming your bloodstream, and they're scanning the barcodes of every single cell they bump into.
Okay, let's unpack this for a second, because it's kind of like a relentless bouncer at a nightclub, right? Just checking IDs at every single door, hallway, and table.
That is a perfect analogy, and this bouncer has a strict zero-tolerance policy.
Right. No fake IDs allowed?
None. When these patrol cells scan a bacteria, they read an alien barcode, they sound the alarm, and they destroy it.
Good. That's what we want.
Normally, yes. But the problem is, when a surgeon sews in a donated kidney, the immune system doesn't understand context.
It doesn't know it's a gift.
No, it doesn't know this is a life-saving medical intervention. It just scans the tissue, reads a massive cluster of foreign HLA barcodes, and interprets it as a colossal, highly dangerous invasion.
So the bouncer doesn't just turn the kidney away at the door. The bouncer, locks the doors, calls in a biological SWAT team, and actively demolishes the entire building.
What's fascinating here is that act of demolition is exactly what doctors call rejection.
Wow.
Yeah. The immune system sends killer T cells to literally puncture the cells of the donated organ. It triggers massive inflammation.
Just destroys it.
Completely. It cuts off the blood supply. The tissue undergoes necrosis, meaning it dies and literally turns black.
That must have been so heartbreaking for those early pioneers in the 50s and 60s.
It was devastating. They hit a wall. The biology was the barrier, not the surgery.
Right. But, okay, if the body's natural hardwired response is to violently destroy anything with a foreign barcode, How are transplants happening every single day right now? I mean, you could just reason with a T cell, right?
No, you definitely can't reason with them. But starting in the late 70s and 80s, we basically figured out how to drug them.
Uh,
This is what we call the pharmacological peace treaty. And the real game changer was the discovery of immunosuppressants. Most notably, a drug called cyclosporin.
Cyclosporine. Okay, let's define what that is actually doing in the body. Because it's not just like a general painkiller or an anti-inflammatory, right?
Right, no, it works at a very specific mechanistic level. So when a patrol cell spots a foreign barcode, it normally releases chemical signals.
Like a flare.
Yeah, specifically one called interleukin-2, which acts like a megaphone, basically telling the rest of the immune army to multiply and attack.
Okay, so what does the drug do?
Cyclosporine steps in and just jams the megaphone.
Wow.
It completely blocks the production of that specific chemical signal. So the patrol cell still sees the foreign organ, but it can't call for backup.
So the army just stays in the barracks.
Exactly. The army stays put.
But, our sources emphasize that this is a really brutal trade-off. Because if you are jamming the megaphone so the immune system can't attack the new organ, you're also jamming the megaphone when a real threat shows up.
Yeah. And that is the permanent, precarious tightrope every single transplant recipient has to walk.
That sounds terrifying, honestly.
Yeah. It is, because by taking these drugs, you are chemically suppressing the very system designed to keep you alive in a world that is just covered in pathogens.
So a normal bug becomes a huge deal.
Right. A common cold, a minor scrape, or, a mild case of food poisoning suddenly becomes a potentially lethal event.
Wow.
And it gets worse. Because our immune system doesn't just fight bugs outside the body, it also polices our own body for rogue, mutating cells.
You mean cancer?
Yes. When you suppress the immune system long term, the risk of developing certain cancers rises significantly.
So what does this all mean? It sounds like we are basically turning off the house's burglar alarm to let a friendly guest sleep on the couch.
Yeah.
But that means we're also leaving the front door wide open for actual robbers.
That is the daily reality for these patients, yes.
Yeah.
They have to calibrate this dosage with their doctors constantly.
That's be exhausting.
It is a delicate balance. Too little medication and the immune system wakes up and destroys the organ. Too much medication and a standard seasonal virus could be fatal.
Which really explains why we hear so much about the concept of finding a match on those transplant waiting lists.
Precisely. If you can find a donor whose HLA barcodes are incredibly similar to your own, the immune system isn't quite as easily triggered.
So you don't have to turn the burglar alarm completely off if the guest looks a lot like a family member.
Exactly. The closer the match, the gentler the rejection response, which means a lower dose of immunosuppressants is required, and the safer the patient is from those secondary infections.
Okay, so we solved the plumbing. And we largely solved, or at least learned to manage, the biological rejection through this delicate dance of barcode matching and immunosuppression.
Right.
But the sources point out that solving those two problems just slammed us into a third wall.
A very big wall.
And this one isn't about complex biology. It's just an agonizing problem of basic math.
Math and logistics, yeah. The numbers are just stark. There are far, far more people suffering from end-stage organ failure than there are available organs.
Right. Hundreds of thousands of people worldwide are on waiting lists.
And tragically, many will die waiting.
Here's where it gets really interesting, but also deeply tragic. We've mastered this medical miracle, but we're entirely bottlenecked by supply. If the drugs work and the surgery works, why is the math so broken? It comes down to how we actually get these organs, doesn't it?
It really does. We rely almost entirely on human tragedy. The vast majority of organs come from deceased donors.
But you can't just use an organ from anyone who passes away, right?
No, not at all. For an organ to remain viable, the donor typically has to die in a highly specific medical environment. Usually they have to suffer brain death while already on a ventilator in an ICU.
Why is that so specific?
Because that keeps oxygenated blood pumping through the organs right up until the exact moment of recovery.
So if someone passes away peacefully in their sleep at home, their organs just begin to break down from oxygen starvation almost immediately.
Exactly. The window of viability is shockingly narrow. In the medical field, this is called cold ischemia time.
Cold ischemia time.
Yes. It's the time an organ can survive on ice without blood flow, before it's basically useless.
How long is that?
Well, a kidney can last maybe 24 to 36 hours. A liver is closer to 12.
And a heart.
A human heart is only viable for about 4 to 6 hours outside the body.
Oh my God. 4 to 6 hours. So you need the tragedy of a sudden death, usually a young and otherwise healthy person happening in an ICU with family consent, followed by this wildly complex logistical sprint across the country in a helicopter.
All to save just one person on a list of hundreds of thousands.
Are we just permanently stuck waiting for terrible accidents to happen so lives can be saved? The bottleneck isn't the medicine anymore, it's the supply chain.
Which is exactly why the sources are so explicit in their plea to the public. Registering as an organ donor and talking to your family about it is arguably the most impactful civic action a person can take.
It really is.
Because one donor can provide a heart, 2 lungs, a liver, 2 kidneys, a pancreas, and intestines. I mean, it is a staggering gift.
But mathematically, we will never bridge the gap between supply and demand if we're relying on human donors alone.
No, the math just doesn't work out.
So that tension, having the medical capability to save a life, but watching the patient die because of the supply chain issue, that is what pushed researchers into a territory that genuinely sounds like a sci-fi novel.
It really does, because if we can't get enough human organs, we have to look outside the human species entirely.
Right. And this field has a specific name.
Yes, it's called xenotransplantation. That's transplanting organs from an animal into a human.
Xenotransplantation. And the animal of choice, which I found somewhat surprisingly in our sources, is the pig.
Right.
Because I think most people intuitively assume we'd look at primates, like
Yeah.
chimpanzees or baboons, since they are our closest evolutionary cousins.
And primates were the initial focus decades ago, but they present massive hurdles.
Like what?
Well, first, they take years to reach maturity and they don't breed well in captivity, so that doesn't actually solve the supply problem.
Oh,
And second, they harbor these really complex viruses that can easily jump to humans.
that sounds dangerous.
Very. Pigs, however, are this kind of biological sweet spot. Their organs, specifically the heart and kidneys, are remarkably similar in size to ours.
Really?
Yeah, a pig heart pumps at roughly the same pressure as a human heart. And pigs can be raised in large numbers, maturing in just a matter of months.
But hold on, wait. We just established that the human immune system will tear apart a kidney from a fellow human being just because the HLA barcode is slightly different.
Right.
If a human kidney causes a biological riot, an organ from an entirely different species must cause, like, a full-blown biological apocalypse.
Oh, it does. It triggers something called hyperacute rejection.
Hyperacute rejection.
Yes, it is much faster and much more violent than regular rejection, and it all hinges on one tiny molecular detail. Pig cells are coated in a specific type of sugar molecule called alpha-gal.
Alpha-gal. I think the full name is galactose alpha-1 giver 3 galactose.
Yes, exactly. And almost all mammals have this sugar on their cells. But humans, and actually some of our primate ancestors, lost the gene to produce alpha-gal millions of years ago during our evolution.
Wait, so because we don't naturally have it?
Because we don't have it, our immune system views alpha-gal as a highly dangerous foreign contaminant.
Oh, wow.
In fact, our bodies are naturally swimming with antibodies specifically designed to hunt down and destroy alpha-gal.
So the second you connect the blood vessels to a pig kidney, the human blood rushes in, the antibodies see the alpha-gal, and what happens?
It's immediate. Within minutes, the antibodies attack the lining of the blood vessels inside the pig organ.
Within minutes.
Minutes. The blood coagulates instantly, forming these massive clots. The organ literally turns black and dies right there on the operating table.
Oh, my God.
And no amount of standard immunosuppressant drugs can stop it. It's just too fast and too violent.
Okay, so if the human body is hardwired to violently reject this alpha-gal sugar in minutes, how is xenotransplantation anything more than just a theoretical fantasy?
The answer lies in the most revolutionary biological tool of the 21st century.
Gene editing.
Exactly. CRISPR gene editing. We aren't just taking regular organs out of regular pigs anymore. Scientists are engineering entirely new lines of pigs at the embryonic stage.
Okay, let's break down how this actually works, because CRISPR is often described in the media as molecular scissors, but it's doing something much more sophisticated than just cutting things up, right?
That's right. CRISPR basically consists of 2 main parts. There's a guide RNA, which acts like a GPS system homing in on a very specific section of DNA.
Okay.
And then there's an enzyme called Cas9, which does the actual cutting.
So it finds a spot and snips it.
Exactly. So scientists program the GPS to find the exact gene inside the pig's DNA that is responsible for manufacturing that alpha-gal sugar.
So they find the alpha-gal factory in the DNA, and they use the Cas9 scissors to just snip it out. They literally delete the barcode that causes hyperacute rejection.
They delete it. But deleting isn't enough.
Why not?
Because the human immune system will still realize it's looking at an alien cell. The structure is still slightly off, so they have to go a step further. While they're in the genome, they paste in human genes.
Wait, really? Human genes into the pig?
Yes. They insert human DNA sequences that produce human regulatory proteins, like specifically a protein called CD46.
What does CD46 do?
Well, in a normal human body, CD46 acts like a white flag. It tells your immune system, hey, I belong here, do not attack.
So by editing the pig genome, the pig organ actually grows up coded in these human do-not-attack flags.
Precisely.
Wait, so going back to our bouncer analogy, this is wild.
Yeah.
It's like finding a foreign, unregistered car that would immediately be impounded by the police.
Okay, I like where this is going.
You aren't just stripping off the factory logos and filing down the serial number so it can't be identified. You are actually bolting on local license plates and slapping a fake city inspection sticker on the windshield to trick the cops into letting it drive down the street.
That is an incredibly accurate way to think about it. We are genetically modifying the architecture of the organ to forge its biological paperwork.
Forging the paperwork.
Yes, we are making a pig kidney look just human enough that the patrol cells get confused, read the fake license plate, and just let it pass.
But wait, I have a question. Even if we perfectly disguise the outside of the organ by editing the barcodes and slapping on CD46, isn't the inside still pig tissue?
Yes.
And don't pigs carry their own native viruses? Like, if we put a pig heart into a human whose immune system is being suppressed by drugs, couldn't an animal virus just wake up, infect the human, and mutate into something contagious? Because that sounds like the recipe for a brand new pandemic.
You have just hit on one of the absolute greatest anxieties in the entire field of xenotransplantation.
I mean, it makes sense to worry about it.
It does. It's called the PERV problem. That stands for porcine endogenous retroviruses.
Endogenous, meaning they are baked in.
Exactly. These aren't viruses the pig catches from a sneeze in the barn. The viral DNA is permanently embedded in the pig's own genome.
Wow. Over millions of years of evolution, I guess.
Yes. You can't just wash them off or treat the pig with antivirals. Every single cell in the pig carries the blueprint for these viruses.
So for a long time, the PERV problem must have been considered an absolute showstopper. I mean, the risk of triggering a cross-species outbreak is just too high.
It was a massive roadblock for years.
So how do you solve a virus that is permanently written into the DNA?
You use the exact same tool, CRISPR.
More editing.
Yes, researchers deployed CRISPR on a massive scale. Instead of just knocking out the one gene for alpha-gal, they programmed CRISPR to hunt down and inactivate dozens of these hidden viral sequences throughout the pig genome simultaneously.
Wow.
They essentially scrubbed the retroviruses out of the DNA before the pig was even born.
That is just an astonishing level of genetic manipulation.
It's unprecedented.
But I want to be careful here for the listener and really ground this. Because when we talk about heavily gene-edited pigs and scrubbing retroviruses, it sounds like highly theoretical lab work.
Right.
Are we talking about an endless drive-through for organs tomorrow? Or is this still highly experimental? Where does this actually stand in reality today? Are there humans walking around with these edited organs?
This is where we cross from theory into history. Because yes, in recent years, surgical teams have successfully transplanted these gene-edited pig hearts and pig kidneys into living human patients.
Really? And what about the hyperacute rejection, the blood clotting and blackening in minutes?
It didn't happen.
Wow.
The genetic disguise worked. The organs were successfully perfused with human blood. They turned pink, and they began functioning.
That's incredible.
The kidneys started making urine. The hearts actually pumped blood.
That is a staggering milestone for humanity.
It truly is. Now, these were profoundly ill patients who had exhausted absolutely every other medical option. They were essentially compassionate use cases.
Right.
And while these pioneers ultimately did not survive for years, they survived for weeks or months, they proved the fundamental concept.
That a highly edited animal organ can sustain human life without being immediately destroyed by the immune system.
Exactly. The fake license plates worked.
But surviving for a few months isn't the ultimate goal, obviously. The goal is decades. What are the hurdles keeping this from becoming a standard procedure tomorrow?
Well, the first hurdle is long-term rejection. Tricking the bouncer at the front door is one thing, but keeping the disguise up for 20 years while the immune system conducts continuous, deep cellular inspections is another.
So you still need the drugs.
Yes, we still have to use powerful immunosuppressants. And eventually, the body often figures out that something just isn't right.
Makes sense.
There's also the question of physiological compatibility over time. Like, does a pig heart age the exact same way a human heart does? We don't really know yet.
And there have to be ethical concerns, too.
Absolutely. As the science advances, society is going to have to navigate the complex ethics of raising genetically altered animals solely to harvest their organs for human medicine. The door is pushed ajar, but a limitless supply of organs just isn't around the corner quite yet.
It's an overwhelming amount to process.
Yeah.
But when you step back and trace this entire arc, the story of transplantation really is the story of an escalating negotiation with our own biology.
Yes, beautifully put.
I mean, we started by trying to force it in 1954, but the body ripped it apart.
Yeah.
Then we learned to chemically suppress the immune system with drugs like cyclosporine. We learned the logistics of matching barcodes to minimize the fight.
Right.
And now, driven by the brutal math of the organ shortage, we're literally editing the genetic code of another species to build organs that can sneak past our own defenses.
It represents both a triumph of modern genetics and an incredibly humbling reminder of how fiercely our bodies are designed to protect us. We are hacking millions of years of evolutionary defense mechanisms. And it's really vital to remember that until these gene-edited organs are perfected, the entire system relies on the profound generosity of human donors. The science is miraculous, but it's built on a foundation of basic human empathy.
Absolutely.
Yeah.
If you take anything away from this deep dive, let it be the reminder to check your donor status and have that conversation with your family. The math only works if people choose to help.
Exactly right.
But, I want to leave you with one final, slightly provocative thought to chew on today, building on where this CRISPR technology is heading.
Oh, I like this.
We've talked extensively about how we are editing pig DNA to strip away animal markers and add human do not attack flags just so the organ survives.
Right.
But if we are mastering the ability to custom design the genetics of an organ before it's even born, why stop at mere survival?
Wow. Yeah.
If we can edit a kidney to be perfectly accepted by a human body, could we eventually edit it to perform better than a natural human kidney?
That is a wild thought.
Could we engineer a liver that naturally filters out lethal toxins that would normally kill us? Could we design organs that inherently resist cancer or constantly synthesize their own internal medicines on demand?
It changes the entire paradigm.
Exactly. If we can forge the biological paperwork to bypass the bouncer, the limit might not just be replacing what's broken. The limit might be fundamentally upgrading what the human body is capable of. Something to think about the next time you feel a heartbeat in your chest. Thank you for joining us on this deep dive. See you next time.